Finally, we'll take a look at a few examples of computer scans in remote operating system detection. We'll start in the lowest layer with the IP scan. Above, you can see a capture file you'd never like to register in your network. We see here that some IP protocol packets were sent, and any packet of other protocols. We're dealing with scanning in the third layer of the OSI model. The attacker tries to probe the network infrastructure in this way. They want to see which protocols are supported by which network devices. This is called the IP scan. Only IP packets are sent in the IP header. They contain information which protocol should be above. Then, you wait for a response from a given device. It will tell you whether the device supports the protocol or not. The IP scan is used to check out the infrastructure of network devices. This is how the IP scan is presented in Wireshark. Let's see how the port scan looks like. We see the TCP packets sent by the computer identified by the address 10.1.0.2 to a computer identified by the address 10.1.0.1. This is very chaotic. If we look at the destination port, it appears that each packet is sent to a different port. Everywhere connection request is addressed to a different port, and each time the destination computer responds with a reset. If the port is closed, the RST packet is sent. That's how the TCP scan works. If the port is opened, it either won't respond or the response will be definite. However, if you receive an RST response, it means that the port was closed. The scan failed. We can see that, in our case, most of the ports were closed. However, if the port was open, the server responded with a SYN and ACK packets. The port wasn't behind the firewall. It tried to establish a TCP session, just as we've discussed it before. In this case, we can analyze successful and failed attempts to establish a session through a standard scan. Let's examine UDP scan. Because UDP is a stateless protocol, we do not expect a positive response. This is a broadcast protocol. The packets are sent, but there is no certainty whether they got through and are received. In accordance with the RFC, after receiving a packet at a closed port, the computer should notify the sender by sending the ICMP packet. Destination unreachable, port unreachable, informing them that the packet was sent to the wrong address. In the UDP scan, no response means that you have come across an open port. At the same time, we expect the error message if a packet reached a closed port. How such a scan proceeds is shown in the picture below. Finally, let's see how you can identify remote operating system. In this case, the ICMP protocol was used. We see the attacker's computer with IP 10.0.0.29 and the test computer with the address 10.0.0.2. The process begins with sending an echo packet and waiting for the response. This is repeated several times because the ping command sends several packets. In this step, we want to identify a computer existing in the network. Then we formulate different ICMP requests. We look at what the requests and how the server will reply. If someone responds to the timestamp request, giving away the timestamp, or not, depends on a particular version of the device and the operating system. Older Windows systems readily allowed to synchronize their clocks. After the request, we see the response. Someone shared with us his timestamp. Then we ask about other things, for example, the IP version 4 address mask. We can receive the response or not. The response may also contain the default values. The process, which has been previously presented and used quietly in a certain program, for example in Nmap, to identify a victim's operating system, boils down to posting a typical or atypical request and observing responses. Individual responses are compared with a list of predefined schemata. Certain systems respond to one kind of questions, other systems to another kind. After you've used up all the 60 questions, you can quite accurately determine what system you're dealing with, details such as version and service pack included. Functionalities we've tried out are only a part of the full capabilities of Wireshark. We had the opportunity to capture some data, configure the display filters. In a nutshell, we went through the features such as visualization, statistics, packet coloring, and creating custom profiles. The range of possibilities offered by Wireshark that we got to know is sufficient to monitor user activity in the network in real time. It allows you to detect unusual behavior of hosts and users and react to it accordingly, for example, by recording a certain operation. If you'd like to analyze safe capture files, Wireshark files are used by various network services, for example, programs for cracking Wi-Fi network passwords. If you have some spare money, turn on Wireshark for a while and send someone a file to a certain web page. The next day, you'll get an email with a password for the Wi-Fi network whose packets you captured. As you see, Wireshark has a very broad application. Before you use the capture files as a proof, you need to sign them. A couple of modules before, we mentioned how important data integrity is. You should sign the file with the SHA-1 or MD5 key. In that way, you can make sure that the data someone extracts from the file will be the data that you have provided to them. At this point, I would like to end the presentation of Wireshark. Thank you for your attention.